In this problem, we'd like to find all the solutions of the cotangent of x plus 1 over 3 equal to 1 on the particular interval 4 pi to 10 pi. Now the first thing we notice is because of the periodicity of the trig functions, there are going to be, in fact, infinitely many solutions here. So the way to go about these problems where we want to ultimately find all solutions on a particular interval is to start by finding all solutions imaginable. So let's go ahead and do that, and remember the way we do that is we introduce a parameter k that is an integer. Let's go ahead and take care of this cotangent by hitting both sides with the inverse cotangent. So when the arc cotangent hits the cotangent on the left here, we're just left with x plus 1 over 3, all equal to the arc cotangent of 1. This is a very particular value. The arc cotangent of 1 is pi over 4. But since we're trying to write down all possible solutions, we need to look beyond that one value. So remember how we do this. We take a 1 period length interval of the cotangent. So what is the period of cotangent? It's pi. And so we need to take a pi length interval. So our goal is to find all values of theta such that the cotangent of theta equals 1 on a pi length interval, say 0 to pi. Now, we could choose any pi length interval we want, but there's some advantages to this. First and foremost, we know that the cotangent function has some discontinuities. Those discontinuities occur at 0, pi, 2 pi, 3 pi, negative 17 pi, lots of discontinuities. So it's to our advantage to choose a pi length interval that doesn't have any of those discontinuities. And so notice this is one such interval. And so what we want to do is find all theta that make the cotangent equal to 1 on the interval 0 to pi. So it's always useful to look at a unit circle. So here's the unit circle. Now we're on the interval 0 to pi, so we really actually only care about the upper half of the unit circle. And we already know that as a function, the arc cotangent of 1 is definitely pi over 4. That's just what it equals. So that angle pi over 4 is certainly a value of theta in the interval 0 to pi that makes the cotangent spit out 1. Are there any others? Well, no, there's not. We get lucky here. There's only one value of theta in the interval 0 to pi that makes the cotangent equal to 1, and it's pi over 4. Theta equal to pi over 4 is the only one we have to work with. That's nice. So this theta equal to pi over 4 will lead to one solution for x. But we're not satisfied with just one solution. We want every conceivable solution. So what do we have? We're going to go from here and find that x plus 1 over 3 has to equal pi over 4 plus pi k, where k is any integer. Now a couple of things to note here. Why did I choose pi here and not 2 pi? Well, it's because the period of cotangent is pi, not 2 pi. There is an intimate connection between this coefficient in front of the k and what the period of the trig function is. The other thing to remember is that the k itself is just any integer, positive, negative, 0, any integer imaginable. And for every choice of k produces one solution of the original equation. And so this expression right here really captures every conceivable one of the infinitely many solutions of our equation. Now let's actually solve for x here. So multiply both sides by 3, we get x plus 1 equal to 3 pi over 4 plus 3 pi k, certainly distributing that in, and subtract 1 from both sides. So x equal to 3 pi over 4 plus 3 pi k minus 1, where k is an integer. This represents every possible one of the infinitely many solutions of this equation. But remember, in this particular problem, we don't care about all infinitely many. We only care about the solutions that live on this interval right here. So now let's reach into this expression that captures all infinitely many and pick out the ones that live on the interval 4 pi to 10 pi. Now, for convenience here as we do this, let me write down what 4 pi and 10 pi are approximately equal to. So 4 pi is approximately equal to 12.5663, and 10 pi is approximately 31.4159. So we're really seeking to find all solutions that live between these two numbers. So what's one way we get one of the solutions out of this list of infinitely many? Well, we take k equal to 0. That's a perfectly legit integer. And this formula up here tells us that we'd have 3 pi over 4 minus 1. So that is in fact a solution of our equation. However, if we run to the calculator, we're going to find that this is approximately 1.3569. Definitely not in the interval we care about. So we throw this one away. It's not where we want it to live. So let's go down the list. Let's find another solution. How about when k equals 1? We know this equation, once again, will produce a solution. Now we plug in k equal to 1. We're going to get x equal to 3 pi over 4 plus 3 pi minus 1, which, doing a common denominator here and adding, we're going to get 15 pi over 4 minus 1. Well, let's run to the calculator again and see if we're in the correct interval. This is going to be approximately equal to 10.789. Again, we're not there. While this is a solution of the original equation, it doesn't live where we want. So we can keep playing this game. So let's try k equal to 2 and see what happens. So k equal to 2, we're going to get x equal to 3 pi over 4 plus 6 pi minus 1. Again, doing the algebra, that simplifies to 27 pi over 4 minus 1, which is approximately equal to 20.20575. That is awesome because 20.2 is in fact in this interval. So this is one solution that we want to keep a hold of because it is where we want it to live. Are there others? Let's see. K equal to 3, we can generate another solution. So x equal to 3 pi over 4 plus 9 pi minus 1 equals 39 pi over 4 minus 1, which is approximately equal to 29.6305. And again, we have success. There's another solution that lives in the interval we desire. Are there others? Let's do k equal to 4. So in this case, we'll have, once the dust settles, it simplifies to 51 pi over 4 minus 1, which is approximately 39.0553. And that's a problem. That's not in the interval. So once again, even though this is a solution of the original equation, it's not where we want. And now we can see that if k gets bigger and bigger and bigger, our solutions are going to get bigger and bigger and bigger, so they're definitely not going to be in the interval. Or if we took, say, negative k, we're going to start getting solutions that are negative, so they're definitely not in this interval. So we've created an exhaustive list. So there are only 2 solutions out of the infinitely many solutions that live in the interval we care about. So the answer here would be x equal to 27 pi over 4 minus 1, or x equal to 39 pi over 4 minus 1. These are the 2 solutions of that equation that live in the interval 4 pi to 10 pi.